Thank you, Raymond.
Good morning, everybody, and thanks for coming. How many of you are experienced Python developers? How many have done API design on your own? All right. So I will aim this in a fairly deep level, and I'm going to try and share with you some of my experiences. I've been privileged over the last decade to be a Python core developer, which means that I had a chance to learn from some of the greats. When Guido was very active, we did a lot of design together. Alex Martelli, Tim Peters, Mark Lindbergh. All of these people taught me to be a better programmer. And so I learned some skills from them that I hope to pass along to you. But there's another set of skills, ways to learn skills, and that's to learn the hard way. They say experience is the toughest teacher. He gives the test first and the lessons afterwards. So after a decade of core developer, we have a lot of things that we did right that I'd like to share with you, and things that we did wrong. And what I'd like to do is have us all learn from those experiences so that you get to be in the position as if you had developed for a decade with the core and learned what they shared with me and learn the things that we learned the hard way. Sound exciting? All right. So I get all of my feedback for the most part from Twitter, and I also encourage people to come to other classes, and I build up enthusiasm for trainings and whatnot through Twitter. So if you were to tweet like a 15-year-old girl, it would make me very happy. Yes. Oh, so at Raymond H is the Twitter feed. There's going to be a test at the end. You guys ready for a test? All right. So it's a real-world test. How many of you came to the teaser talk yesterday for Advanced Python? Okay. So I will do a brief review of a bloom filter at the end of this, and recapping what I did yesterday. The bloom filter recipe that I circulated on Twitter and mentioned on Python Dev and whatnot was very popular. Lots and lots and lots of people looked at it. It's got circulated around Hacker News, and I got a number of requests. Would you put this into the collections module? So it makes sense to go into the collections module in the sense that it's something that a lot of people would have a use for. It's educational, and it'd be really nice to just have that tool at your fingertips and not have to download it. But before it can go in, it needs to prove that it's worthy. For it to be worthy, it has to have a good API. API design, I think, is not that easy. So the test for today is we will bring up the bloom filter and tease out some of the API design questions, and possibly in class design the API for the bloom filter to go into the collections module for Python 3.3. How's that for a test? All right. Now, if you haven't done core development before, you'll know how important this test is, because as soon as you put it out, the API becomes locked in. We can't change it, and for all eternity, if there's something wrong with it, I'll be able to point back to the reason this API is messed up is because this class failed its test. No pressure. All right. Is there a one true answer to the correct API? The principles I'm going to give you today are really, they show a balance of forces. I think almost every time I hear a design principle says you have to do something this way, it is almost always wrong. The real answer is that sometimes it's a good idea, but it's overpowered by another conflicting goal. You list out all the desiderata. They don't all point in one direction. And the correct API really depends on context, who's going to be using it, where it's going to be used, and that sort of thing. Sometimes you have principles correcting you towards simplicity. Do the simplest thing that could possibly work. Sometimes you have a principle pushing you toward completeness. Provide a complete API, because if you don't, your users will complete the API for you, and they will all do it in different ways, in ways that lock you in so that you can't make changes in the future. So simplicity is not always a correct design principle. Sometimes you get the simplest thing that works, but the simplest thing that works is a set of functions that are blocking, which means that as soon as you give your API to users who are trying to build a non-blocking I/O and whatnot, you have interfered with your ability to make highly efficient Python programs. And then there's the balance of ease of use versus flexibility. Alex's talk, how many of you went to Alex's talk first day? So you learned some of the API anti-design anti-patterns, and his goal there was to help you go forward and shed some light on API design by saying, here, if you don't do this, you do the opposite of this, you'll end up with a good API. I think some of those principles kind of left you hanging, right? One of them was, well, at least have an API and at least attempt to design it, which is fantastic advice, except that it doesn't tell you what to actually do. So we're going to go into that. So first, I want to talk about the environmental considerations for choosing your API. That is the context that determines which principle wins. So one environmental consideration is if you have to have an API that conforms to a spec. At that point, your hands are tied, but usually tied in a good way. So the FTP lib, for example, corresponds very closely to the RFC or the FTP protocol. And so that API is exactly what you would expect. It's someone that coming to Python from another language which used a FTP library would already know how to use it because the methods they expect are there. So conforming with the spec is a fine thing. It improves learnability. Again, somebody coming from another who has had experiences with another tool and then comes to your tool, if you could design it in a way that they already learn it, know it, and have a zero learning curve, you really help your users quite a bit. So one example of where our hands were somewhat tied was the decimal module. Decimal module, there is a spec, and we decided early on we were going to comply with the spec 100%. On the theory that a large number of people put a lot of effort into hammering out the spec and making it consistent and usable, and that there were working implementations in other languages. In addition, the spec shipped with tests. There were, I think, upwards of 100,000 tests already made. That's fantastic, because then you can tell right away whether what you've made complies with the spec. The downside of this is this spec has a horrendous API. Who of you have used the decimal module before? Okay. How do you round something off to 2 decimal places? There's a method for it. Yes. And it's called quantize. It's not called round. And quantize takes an argument. So to round to 2 decimal places, what do you think the argument would be? Number 2, right? No, you actually give it the argument 0.01, which is a pattern that it should quantize to, like a snap to grid. So to round to 2 decimal places, it is number.quantize 0.01. Who thinks that's a fantastic API? Our hands were tied by the spec itself. Another consideration is whether there's a well-known metaphor or some other external expectation about what the API would look like. So I was helped by this when I developed sets for Python. The great thing about sets is we made an effort to not put anything in there that didn't comply with the known metaphors of what you had already learned in school. And sets are also have their underlying implementation is very much like dictionaries. So whenever I present sets, I present them after dictionary. If you look at the Python tutorial, you'll see a big section on dictionary. Right afterwards, there's a section on sets, and I think it's 3 paragraphs long. It's something a person flies right over without even realizing they put effort into it. What's the learning curve there? 0. I never get bug reports on sets, or at least not the core API. I get some for people trying to do very exotic things like sets of non-hashable things that want to mutate themselves and refer back to themselves. I get that. But the basic set API, we never get a question for. No one ever asks about it on the Python tutor list, and the reason is people just get it. And I consider that to be an API success. What's that?
Or they don't use it.
Or they don't use it. So, how do I know people use my APIs? Because there's a so one validation you can get for your API, at least for developing for the core, comes in the form of bug reports and feature requests. So you get some feedback there. I get another form of validation of the API when I go to teach classes or I do consulting. If I go to consult for a company and do a code review for them and find out that they are horribly misusing sets, then that tells me I had an API design failure. But really, one of the most important tools available to me and available to you is Google Code Search. Who's ever used Google Code Search? All right. This is a fantastic and underused tool. I wrote a quote, I think you mentioned yesterday, a famous quote. It's amazing how 3 months of intensive research will, in our time in the lab, will save you 15 minutes of research on the web. So API design, sometimes you're facing problems that have already been solved and solved well somewhere else. And that somewhere else is often not local. So one of the things I do in Python when I'm looking to design an API, let's say itertools, for example, the goal there was to create an iterator algebra, a set of tools, atomic tools that can be composed together to make more powerful tools. I was not designing this from scratch. It's been done before. So I looked at OCaml, looked at Haskell, looked at a number of tools that had some iterator algebra. I borrowed from their ideas and then turned them into a Pythonic form. So a good technique for doing API design is to first search to see how other designs have been done in Java, for example. But then after you publish the API, you can use Google Code Search and actually see how people have used the tools that I've made. So do I know if sets are being used? The answer is yes. I can scan for them. Every one of you who publishes code is making it available so that Google Code Search can come in and tell me how you use the tools that I made. It thinks it's fantastic. It's an excellent and underutilized design. So one other design consideration is how broadly published your API is going to be. So with the Python core, we are in a particularly challenging situation of as soon as we publish an API, it sets in stone. It is in concrete, and we have a very difficult time changing it. Deprecations are a horrible, horrible thing to do to our users. So it is better for us to publish a minimal API, let users figure out how they want to use the objects, and then slowly expand the API than to have made a wrong guess at first and take it away. So we have a real tough consideration. Let's say you're designing an API for internal use amongst several of your colleagues. You are in the opposite situation, so this environmental consideration would push you in exactly the opposite direction. And the exact opposite direction would say, go ahead and publish a full API. Try and make it as usable as possible. What I do when I have an API inside a company is I go ahead and just put together the first thing that works, that looks like it's a comprehensive API, publish it out to my colleagues, and they start using it. If later I want to change the API, grab it's my friend. I search through the entire code base and I change every place that it's used. I have the luxury of being able to change the client code. I've offered an API, but I also get to change the code that uses it, meaning I have some more flexibility in changing it. And so it completely changes my approach to API design. We'll see more of that coming up. So you kind of get the notion that the right answer, which I like to put a little trademark symbol out there, the right answer to you, very much depends on the environment that you are publishing. Well-known metaphors, specs, how broadly your API will be used. So let's get into some of the details. So the theme of some of these slides is going to be this opposing forces. Those are the two arrows. One pushing one way, one pushing the other way. A lot of these slides will be in this context. So here's what we want. We have an array, a list, and we want to index into it. It'd be really nice if 3L worked, if a long integer worked just as well as a regular integer 3. We didn't mind if you put 3.0, because 3.0 is equal to 3, which is equal to 3L. So that would be the niceness. However, in order to get that 3.0 or the 3L into a 3, we were coercing it with a int. And so that meant that someone could enter 3.4 and it would round it down and truncate it to 3. Which was grotesque. It was an atrocity, and really we might have been masking a bug in your code and made it to where your test passed, but later your code would fail when you hit a corner case that didn't match the situation you tested for. So this did not bother some people, but it bothered Cleo. It bothers Cleo, it bothers you. bothers you and bothers Guido, it's going to change. What did we do? We stopped using under anti-coerced numbers. We introduced a new API called under index. Who's ever heard of under index? Okay, very few. So what under index is something that you can attach to any object. It's a magic method that returns an integer. So it tells that object, if you would like to be usable as an array index, here, convert yourself to an integer, and then we'll use you in order to look things up. So we were able to take long integers and add an under index method and say, here's how long converts itself to an int. We went to float, and we didn't put an under index there, so that you wouldn't accidentally be able to use 3.4. So that's S equal range. Yeah. Let's see what S3 does. The expected thing. 3L. 3.0. No, doesn't work. Why not? Sure. 3. Let's look on this list, and we see an under index method. Everybody is not being right there. Under index method. And we look on float for 3.0 and no under index method. You learn something new. All right. How actionable is that? Is there a principle to be learned? Yes. When you need to force multiple equivalent input types into a single type, you want to tighten it up. Make sure that unwanted types don't accidentally get caught in the mix. In this case, the unwanted type was the float type, which didn't make sense as an array index. And when we were coercing the int, we were coercing way too much. For instance, what are the things that you can coerce with int? How about this? OX 3P 6. What will that do? Yeah, I thought it actually would do that for me. Let's try it. So let's just try a string 3. So if I was using int on an input before I used get a lookup into an array, I'd actually even be accepting string inputs. Int accepts a lot of things. Some of them are a little bit shocking. Like I can enter strings that include the Arabic intic digits for 42. So they aren't even in the range of ASCII, and it will accept that and coerce it integers. Can you do that?
Does it come with Roman numerals? I'm not really sure.
It does not accept Roman numeral literals. I rejected that PEP. There was a PEP for, to introduce Roman numeral literals into Python. It was issued on April 1st, so it was an April Fool's Day joke. It sat open for a couple years, and when I was closing open PEPs and said, we need to reject this one for this reason, reject this one for this reason, and then I gave a detailed list of reasons that the Roman numeral PEP was to be rejected. I published it on April 1st. And an amazing number of Python core developers stood up to the defense of it. Missed the point. And took me where it said, to remind me that it was a joke possibly on someone. Yeah. All right. Don't take yourself too seriously. So that was the design principle. When you're accepting multiple input types, be sure to screen out things you don't want. It was a mistake we made. Since we made it and learned from it, hopefully you've learned from it and won't do the same thing. It could happen to Guido, it could happen to you unless you're thinking about it. Designing for subclass. There was some cute little story I had heard when I was a kid about a fellow who was playing a fiddle in a house with a leaky roof while it's raining and water's pouring all around him. He said, why don't you fix your roof? And the answer was, well, I can't. It's raining right now. Well, when it's not raining, why don't you fix your roof? Well, at that point, the roof's not leaking. There's no rain coming. The equivalent for us is whenever we design a class, At that moment, we have no need to subclass it. There is no reason to fix the roof. So one of the number one design mistakes that I see in making classes is that people too early say, I'm done. I have a usable class. I would say you are not done unless you've attempted to subclass your class and try and extend it in some way. Very quickly, you'll find some rough edges that can be filed off easily. Did you use super init when you and your initialization function anytime you call a parent class? That's really helpful for subclasses. Did you protect your internal methods? And I'll show you how to do that. Who's ever used the underscore naming convention for a method to indicate that it's private? Who's ever used the double underscore? I'm not saying under name under, which is a private internal name for Python for a magic method. I'm saying under name. Okay. That's fantastic, because I think it's an underused feature, and hopefully after this class it will become much more highly used. It has a specific purpose. And its purpose has a lot to do with subclassing. So let's talk about a problem in Python itself, and why that problem is there, and why it has to be there. So you want to make yourself a dictionary that has case insensitive. This is a reasonably common intermediate level Python exercise. So you override under set item, and or rather extend it. And when you extend it, you uppercase the key and then save the uppercase key. Then you do the same for under get item. When someone does a key lookup, you uppercase it and reach into the dictionary. A very simple intermediate exercise. Who's done something like that before? Who was surprised then that the update method didn't respect your subclass, and then it bypassed it, and it allowed lowercase characters to get in as keys. Dict pop didn't work anymore because it accepted lowercase keys. That's kind of a bummer. Does it sound like a bug in Python? Who thinks it's a bug? No, it's a known purpose. Because ideally, we'd like to have it so that you could override or extend just two methods and then have all of the other methods follow along. But then we have to document the internal relationship between those methods, because who's to say which is the primitive method? Is pop the primitive method, or is get item the primitive method? This contains, some implementations of dictionaries contains is based off of get items, and others it goes in directly. It depends on what's most efficient for a given implementation. So we would have had to expose the internals. Is exposing the internals a good idea? The other reason, though, has to do with the internal invariants. Underneath the hood, there's a hash table, and there are this size of the hash table is known. When you compute a key, the hash is taken modulo the size of the table and indexes into the hash table. Okay. Just the basics of hash table design. If someone were able to override set item and do something that changed the length of the table, and a get item came along and didn't know about it, it could potentially, as a C function, set fault your dictionary. So we say that dictionaries have internal invariants, that all of the methods keep these invariants constant. Whenever you pop, that the length of the dictionary is reduced by 1. And if someone overrode pop and didn't change the length, they could perhaps destroy your dictionary. So what we did was protected all the methods and made them where they didn't depend on each other. So that when you overrode one, you didn't destroy the invariants. So when you subclass a dictionary, it's kind of a pain, but you really need to take every method that is potentially going to change functionality and override all of them. Does everyone see why? We have invariants, we have to protect them. We have to protect them so that you won't be able to cite fault Python itself. And the other reason is we don't want to expose the internals, because as soon as you expose the internals, you lose the ability to make updates. Fair enough? Two opposing forces. That's why dictionaries are the way they are. You learned something new? Okay. So if you're doing your own class design, you will have to consider whether to protect your internals or not. Are you going to make it to where your users can extend a method and just potentially destroy your class? Sometimes that's a good idea, and sometimes not. In the case of CPython, not, because we have so many different types of users with different needs. Seg faulting is really not an option. But for your own classes, it might actually be useful to have one method labeled as, here, extend this, and it will change all the other behaviors. It can become a documented part of the interface. Well, we've done it ourselves. Who knows about the Android missing method? Cool. It's not relatively unknown. So I make a dictionary. I go to look up the key that's not there, M. And what do I get? A key error. It would be really nice if I could intercept that key error and inject an additional behavior. Alex Martelli would say the principle that's being used here is we provided a hook so that someone is attempted to monkey patch your class. So the hook is, let's intercept what happens when there's a missing. And we did that through the underwriter missing method. So what is really happening is for a dict subclass, if a get item looks up a key, doesn't find it, it calls the underwriter missing method with the key as an argument. So let's make a class D, which is a subclass of dict. Define underwriter missing. Takes the key argument. This will get called only when a missing key is being looked up. And let's print did not find key. And let's supply a missing value, perhaps return 0, make a dictionary that defaults to 0. I can even insert the missing key into the dictionary and say self key equals 0, which is different behavior than just returning 0. Actually inserts the key in the dictionary. So let's do one that inserts. So now when I make an instance of D, let's repeat this, and we will no longer get a key error. Instead, the underwriter missing method got triggered. Is there a design principle here? Yes. One is to provide hooks into your function so that you have hardwired behaviors so that your users have some option to extend your class. We'll come back today to several variants of that theme. It is referred to as the open-close principle, OCP. OCP has been stated in different ways by different major authors at different points in history. So there is no one open-close principle. It means different things to different people. But the core concept is simple enough. Open-close principle means you design your classes so that they're open to be extended, but they're closed for modification. And so the class internally respects its invariants. It doesn't get modified at all, but you provided hooks to extend it. And Alex would tell you, always provide hooks into hardwired behavior. Otherwise, you're forcing people to rewrite classes that look just like yours. So if we learned something new with underwriter missing, that's fantastic. So if we provided a hook in to provide control access to what happens, but we did it in a way that a person would not be able to damage the dictionary itself when we left all our invariants intact. Yes, sir?
But I would have the need to set a key if it's not existing. I would use set default normally. Doesn't this method some way touch there's only one way to use it? Or one of this?
Okay. So one of the design principles for Python, one of the pieces of Zen is there should be one way, obvious way to do it, and that way isn't obvious unless you're Dutch. And set default was proposed by someone who was non-Dutch. And so to Guido, that was not an obvious way to do it, and so he went into Python. And it is a hideously named method. Very few people have an instant intuitive understanding of it. It's not particularly efficient, although it does have one magic power that kept it alive. I tried to kill it for Python 3 to rip it out. Who knows what the magic power is? It does something that no other alternative, like underwriter missing, default dict, we have a third variant. There are several different ways to do this. Underwriter get. Its magic power is its atomic. So you have pre-created a list as a default value. In one step, you can one clock cycle of Python's internal loop, where it's executing opcodes in a single cycle, It will check the dictionary to see if a key is present. If it's not, it will insert your new object into that dictionary and return that object. Meaning that you can write multi-threaded code without using blocks, where you can add a new task to a dictionary, a new task list, and then another thread can come along and be running set default also, and you'll know that they won't stomp on each other, and you won't have a race condition between them. Is this item already there? And if it's not, I'm going to put one in. That is a race condition. If you can join the two together, that's its magic power. You can learn something new. All right. And that's why it still exists. Under missing is the general purpose way of doing it. So we introduced that and said, hey, this is a good general purpose tool. What was the problem with under missing? Well, it's general purpose. It solved all needs. Yet the real world encountered it, and an amazing number of people read about it and didn't use it and promptly forgot about it. Even Python heavyweights, people who teach Python all the time, would occasionally come along and say, you know, we need some type of variant of a dictionary that can have default values like 0 or a default word creates a new list. It's like, we've already got one. Really? So people tend to forget about it. There is something about the design of under missing that causes a lot of you appear to be expert Python users. You use Python every day. Claim to have been advanced Python users. You seem to have known a number of things that advanced Python users know, yet most of you didn't know about under missing. That tells me that something's wrong with that notion of under missing. We don't know what's wrong with it. We just know that somehow it doesn't stick in people's minds.
There's something missing with missing.
There's something missing with missing. Okay. So sometimes there is a lesson to be learned, and we don't know what the lesson is. All right.
But is this quality in Python designed to be used by the subclasses for data types?
So the question was, is this the only thing in Python designed to be used by subclasses? And the technical answer is yes. However, the reason I arranged for it to be that way is it makes no sense for a dictionary itself, a regular dictionary, to have an under missing. And so from your point of view, it's as if it worked for both the superclass and the subclass.
I mean, it's reasonable. Remember it.
Oh, I see. The reason people don't learn it is when you're first learning about dictionaries and you hear about it, it doesn't matter to you because no one thinks about subclasses when they're thinking about a superclass. It wasn't raining when I learned dictionaries. Yes, sir?
I will tell you why some of us don't find missing easy to remember. It's when we learned about dictionaries, you couldn't subclass them.
Oh. Yeah. So, back in the old days, when men were men, giants roamed the plane, there were lights on the front of the computer and switches. We saved our programs on paper tape punch, and we were happy. We didn't need no under missing. Okay. All right. Let's see. Oh, yes, there's something important on the front for it. The double underscored methods. I promised you to tell you what they're all about. So internally for a dictionary, if you override a set item, nothing else for dictionaries that uses set item, like update, will change. What if you were designing your own dictionary class and you made a set item? What if you would like to have this type of design too, so that if someone overrode set item, it didn't change the update? How would you do it? The answer is a double under. So let me show you this technique. Create a new class. And it is your dictionary. You're going to define all of the usual dictionary methods, including you're going to define set item. Later, you're going to write an update. Let's say something that takes an items list, not the full interface for this. It's a for key value in items. K equal V. This is a very obvious way to write this code. Now, someone other than you comes around and they're writing a subclass E. And they do a def set item and they are changing the behaviors in some way. When they've done that, they have changed update also, because your update calls a set item right here, and that set item will be this set item, not the one you wrote. So possibly you have done harm for your user because they've subclassed one and they said, I've changed set item, why did everything else change? If in your design you'd like to protect them for that, what would you do? Just like this. Local set item. Equal to under set item. I've now made, this would have been much cleaner looking if I did not a magic method to do this with. So because I started this with 2 underscores, it's going to be name and made unique to class D in a way that is not visible to class E. So I have 2 copies of this function. So down here, so under local set item. So what have I just done to my code? I've made it to where update, when update runs, it calls the local set item, the one that's part of D, not the one that's part of the user class E. That emulates the way Python's own dictionary is set up. In that way, you can guarantee that your internals are protected and that if someone changes under set item, they won't destroy your whole class and break all the variants. We would say that your class is open for extension. Somebody can still extend set item, but it's closed for modification. It doesn't modify the whole class. You learn something new. That's what the under is for. Use it a lot. This technique is dramatically underused. I'm looking at the source code for Python itself. Let's look up the ordered dictionary. There we go. By initializing an ordered dictionary, I can pass in a list of key valued pairs. It will save those and remember the order. Who's ever used an ordered dictionary? For those of you who haven't, it has the exact same API as a regular dictionary, except that it remembers the order that the keys were inserted. So if you insert key A, B, and C, they will list out in the order A, B, and C. They won't scramble like usual dictionaries do. So init, when you take it the list of pairs, it calls its under update method. Because update has exactly the same API as init. I protect it by using the double underscore. You see the double under here? Really interesting. Something is going on the screen that causes it to highlight in a very different place than I'm pressing. Huh. And I told this yesterday that science just starts with the question of, hey, gee, that's funny. There's some science, there's a discovery to be made here. Okay, so this is the important part. I didn't call update directly, I called under update. Now, down below when I define update, which I brought in from another source, so to bring in the copy of update from mutable mapping. So I didn't rewrite it, I copied it from somewhere else. So at this point, update is defined. But I made a local copy of it with under update equal update. That way, subclasses can override update without breaking init. The expectation of a subclasser is if they extend update, they don't expect the whole class to break. I wasn't expecting a well-known Spanish Inquisition. So you got it deeply. We use it in the core. You should use it often. This is a underutilized technique. Why is it underutilized? No one thinks about rain on the day where they're building the house and it's not raining. I contend that your class design is not complete until you've thought about subclassers. One way you can protect your subclassers is say, what methods might they foreseeably extend, and if they do I want that change to propagate throughout the whole class or not? If I want it to propagate, I do it the normal way. If I don't want it to propagate, I need to protect the class and use double underscore method. Fair enough?
We could learn something more. Could you go back to your...
We can learn something more. Can you move up to top to your init method? Lower, lower, lower. Could you elaborate why you don't do if not has utter self another root, then self root, but use the try except pattern?
There's a reason behind it, I'm sure.
There is. So the question is, I had two choices of approach here. We list them in the glossary, the EAFP and LBYL. Easier to ask forgiveness than permission, or look before you leap. Look before you leap says, I'm going to do an if has adder in order to go forward. Or the easier to ask forgiveness than permission approach is to just try and see if it's there and catch the exception. And I am trying to remember what governed the difference. It might have actually been an efficiency thing where adder was too slow. Also, I hate has attribute because it's implemented in terms of get attribute, and underneath the hood, the way it works, has attribute. I guess.
Isn't this just about name mangling?
Isn't it about what?
Name mangling. Because you're using double underscore, right? So as after
oh, yes, right.
Yeah, so this is about name mangling.
Okay, yes, so that is the right answer, but I'd actually like to continue with the...
Wrong answer.
It's not necessarily the right answer. The thing that I hate about has attribute. But it turns out there's two things to hate about has attribute. So I only recall one. If has adder some object, we're going to write our own. And it goes like this. Try get adder object that means except attribute error. Return false. Otherwise, return true. Who finds that to be grotesque? I do. And so I don't use as adder because essentially what it does is to try except. But in addition to that, there was a second reason you pointed out, which was the reason I actually had no choice in this case. And the no choice is the under root does the name mangling, and has adder is not able to do that. So I wouldn't get the same effect. I wouldn't actually be able to ever find root, so it was my only choice. Does that make sense?
You can mangle it yourself.
Or I could mangle it myself, which would be wrong. Why would that be wrong? Because the pattern of the name mangling is fairly obvious when you take a look at the class. Let's make one real quick. So you could do it yourself, but it is subject to change. It's not a guaranteed pattern, so class. Okay. Set under root one, here A, and it shows up. So you see the name got mangled. What am I highlighting? It's just brutal. Okay, so laser pointer down here. This under the root got mangled into under A under root. So that's how it achieves the localization to a particular level of the class structure. Okay, so our learning points, the things we just learned new. These aren't API design principles, but not everybody in the room knew, and I didn't recall. Is one that has adder doesn't work with name mangling, so you have to do a try except. And you might as well do the try except anyway, because that's how has adder is implemented. But I don't want to lose the overall reason that I came to this code to begin with, is that you use the under to protect things in the class that have an invariant associated with them that you don't want a subclasser to be able to touch. In addition, Python, we say Python is a consenting adult's language. We tend to leave our classes wide open so that someone can touch the internals of the class in its internal state. I try to not do that and actually hide the internal state. Under the root, I am saving the internal structure of language. The reason that I did that is so that I had some freedom to change. It was not entirely clear what the one true best way was of implementing ordered dig. So by making those pieces private, I've made it possible to, in the future, change the implementation, which in fact I ended up doing because it turned out to be a reference counting issue with this particular design. I actually switched to, in Python 3, the same code, instead of using a list here, uses an object where I keep a weak reference to that object. And it seems to work much better for people who do weird stuff like making order digs that are self-referential. So right now in Python 2, if you make a self-referential order dig, you're complicating the heck out of the garbage collection stuff. Fair enough? So hide your internals so that you're free to change later. Otherwise, if you expose your internals, people can get to them and you won't be able to change them later. Now, just marking it as a private method might have helped, but using the double underscore was a very clear message to everybody who sees this class. Do not rely on the internals of the ordered dig. No, that was a Guido decision. He's just like, go ahead and double underscore and hide the internal state. Yes, sir?
Can you just do the name mangling yourself explicitly? I mean,
Yes, you can.
Include the name of the class in the variable.
Yes. At that point, though, so I have protected a person from accidentally shooting themselves in the foot. However, if they special order a cannon, have it aimed at their foot, sign a waiver, and say fire, I am happy to let them blow their foot off. So, yes.
You don't need to use the double underscore because you can do it manually. And
why would you do that if we provided you this tool that does it for you for exactly this reason?
Because it's more explicit, it shows what's happening and it's not magical.
So, is it more explicit if you invent your own name mangling procedure, or is it more specific if you use the Python's one true way? I'm going to vote on the side of the one true way. Otherwise, we would have just taken it away and not provided it. We would not have put it in the language to begin with. But that's really a personal choice. Really, when it comes to explicit and not explicit, taste vary.
You also like to change the name that you open as your hierarchy.
Fair enough. Okay. Recursive repr. So, as soon as you make yourself an ordered dig, some joker's going to come along and take that instance of the ordered dig and save it as a value in the dig so that you have a self-referential dig. It's just guaranteed. People do that sort of thing. What happens when that happens with a regular dictionary when you do that? How does this repr change? Let's take a empty dict D. Let's add in 1K. So that's the repr for it. And how does that get built? You can make the repr by starting with the items. And then you can loop over that and do a join with a colon space so that we can put the colons in between each piece, and then wrap the curly brackets around it. It's a very straightforward implementation of repr so that we can get this string back. It's the one obvious way. What happens then when the person says D at P is equal to D itself? What just happened to our simple repr function? It fell into infinite recursion. So Python's way of handling it is it recognizes the infinite recursion and puts in a ... Save you from shooting yourself in the foot. Possibly you have a legitimate reason for putting it in there, but we don't want our repr to die the horrible death. Which means the simplest way to write a repr for a class is often the wrong way. So you can build in some custom logic for it, which is kind of a pain in the behind. It takes your simple 3-line repr function and turns it into a 10-line repr function. That's no fun. There must be a better way. And there is a better way. I provided a decorator called recursive repr. You put it in front of your repr function, and it adds this capability. Let's watch it in action. Let's call up. Oh, here we go. Python 3.3. How many are using Python 3.3? You know we have a daily build. You could actually be working with this every day. Why not work off the head and live large?
Is there also an auto of them like Chrome?
No. That would be a step. All right. All right. So I have this simple repr function for the ordered dictionary. It's 3 lines of code. The only reason it's 3 lines of code is I was able to add this repr. Oh, hey, now it works. You can highlight. So I put that line in, and what it does for me is it wraps this in something that detects a recursive call that's in the ... We learned something new. All right, so it's a nice little tool, and this is a good example of what decorators can be used for, how they simplify your life rather than complicating it. So here's the problem. What would be really nice is if I didn't have to put this open paren and close paren there. It's possible to write a decorator that didn't require one. Who's ever written a decorator before? So you know you have 2 different options. One way you can build it. One takes arguments, and one that doesn't. The one that doesn't is kind of plainer, so you don't have to put the open paren and close paren beside it. Any ideas on why that's there? Okay, that's logical. For some reason, I want to pass an argument. What could that argument be? Yep.
That argument may be a function.
That argument could be a function. Anything else the argument could be?
Change you've already dealt with.
No. All right, there's a principle here. Our problem is that I'd like to write something simple like that. I think this looks cleaner and more beautiful than the other way. I'd like to write this and get some output like a : ... for self-referential. However, ... is hardwired behavior. What if you want something other than a ... There are slight variations in how a list repr, recursive list repr displays than recursive dictionary repr. There are various choices here. So in the dictionary repr, it doesn't just put ... it puts curly brackets around it. For list, it puts square brackets around it. What's going on here is I didn't want to lock into the definition, the ... If I hardwire it, I've immediately crippled my user's ability to change the behavior. So Alex would tell you, as soon as you do something like that, what are people going to do? They're going to monkey patch your function, they're going to subclass it in weird ways, they're going to reach and grab its internals. You're going to force your users to commit atrocities, and commit atrocities in a way that you later won't be able to change this function or update it. The correct thing to do is provide a hook. And so what I did was provide an option here. Where does that come up elsewhere in Python? In the beginning, a long time ago, we gave us a center function for strings. Oh, hello, dot center. That centers hello in spaces. These little specks right here are important. See it in the middle? What was wrong with that? We hardwired the space. So Raymond came along and applied the design principle. So this is a Raymond. Are non-breaking spaces. If you're emitting HTML or all kinds of good stuff. Okay, so the principle is here is thou shalt not hardwire behaviors but provide hooks. Possibly, it's nice to have functions that have just 1 or 2 arguments. It looks prettier that way, but the correct way is often the 1 or 2 arguments plus a whole lot of defaults so that people can control the behavior. You learned something new? All right, so now it should be obvious why I required those parentheses, and I did it so that we didn't hardwire behavior. Yes, sir?
But couldn't you have had, well, you could have had something evil, where a recursive repr could have by default, if it examines the type of its first argument, and if its first argument is a function, then it uses the hardware default of ... And if its first argument is a string, then it returns the function that the current one returns.
So, there was a time when I was an accountant, a certified public accountant, a chartered accountant in other countries, and beginning accountants don't get to account. Beginning accountants get to photocopy. So I go from one client to another, and I do a lot of photocopying early in my career. In theory, getting smarter so that the next year I could supervise people who were copying pages. So different clients had different copiers. The best clients had copiers with feeders. So I put a document in, and it'd start copying, and then somewhere through there'd be a paper jam hole. Now, the logical thing to do was I pulled out the papers that had already copied, cleared the paper jam, put the remaining ones in, and let it continue. And that worked just fine for the first few months. Then, I went to another client, and they had a new copier. And the new copier, when I did that, said, you know what? I'd gone down to page 60 before the paper jam. I remember that. And then cycles back through the deck and goes down 60 sheets. Not copying them, it starts on the 60th page. Now, there's nothing on the front of the copier to tell you that it did that. As soon as it was trying to be helpful, but when they started to outsmart me, they got harder to use. So one of the design principles in there is that you need your behaviors to be recognizable so that a person can anticipate what it's going to do. Python programmers are by and large a very clever lot. If they know clearly what your object is going to do, they can do a lot of great stuff with it. But if it starts to get magical, if this argument comes in and it's a string, if this thing is missing, if it was really a function that came in, I'll decorate it. If it's not a function, I will treat it as a string argument and then wrap it. And at that point, you've created enough confusion to where it's starting to outsmart them like the copier. Do not make your objects too smart or too clever in that way, because they become harder to use even though you're trying to help your user. Fair enough? All right. Who's ever heard of tit for tat? Okay, so tit for tat was a program that was a solution to the game Iterated Prisoner's Dilemma. And many people from around the world submitted solutions to this game, and the games were played off against each other on a computer, and the winning game was tit for tat, or the winning strategy, rather. And we learned several principles from its behavior about how to interact with other programs and other people. For example, this is modeled on a human situation, prisoner's dilemma. And these are principles for living, and these are principles for program design. So, tit for tat had the properties of it was always nice first. It tried to cooperate. It was also provocable. If you didn't cooperate, it would immediately reply in kind. So if you crossed them, so you cross me, I'll cross you back. So it's provocable. So be nice and be provocable. But then the third principle we learned is that once provoked, it didn't stay provoked. It only held a grudge for the very next iteration and not in perpetuity, because things that held a grudge in the end performed worse than ones that didn't. So we'd say be nice, be provocable, and be forgiving. So those results were published, circulated all around the world, and a few years later, they had the competition again. Now everybody knew what the winner is and who they were going to be fighting against. New programs were submitted. Who won? It was tit for tat. Now, what was going on is that these programs already knew the range of other programs, so they tried to figure out who they were playing against. Oh, I can always trust Larry. That Andrew, he always crosses me. This person's playing tit for tat. And as soon as it started to make guesses about what the other guy was doing, it became unrecognizable in its own behavior. The other program couldn't figure out whether it was going to be nice or evil, so it always chose the evil option. So the principle out of that is how you behave needs to be very recognizable to another person. You've got the two prisoners sitting and they can see each other through the glass. And I look over and my wife's in the other room. I'm like, she's not going to cross me. And if I look over and she's thinking really hard, at that point I get worried. Just the thinking hard causes you to worry. If you design the intelligence in your objects and try and make them smart, you stop making their behaviors recognizable, and when they don't become recognizable, people assume the worst. It's a principle of API design. Okay, but back to the one on the slide. Hardwiring your choices will severely limit your options for users, so always provide optional arguments for flexibility. But remember these principles? Which ones apply really depends on context. So this is not true in some cases. If I control the client code, if I'm both the supplier of the API and the consumer of the API, all my colleagues are using it, the better thing for me to have done was to make a recursive reference without the control on it. That way people can, I will have made the simplest possible thing that could work. People use simple, clean code, doesn't have little brackets on it, makes the unnecessary call. And all is well and good. But if someday it turns out we need it, I can grep through my code and change all of the uses. So when I have control of the code, the best thing to do is make the simplest possible thing that can work. If there's going to be, I can't control the code, the best thing to do is to provide hooks. You see the balance there? So the top principle doesn't always apply. So if you take something away from this class, it is to take everyone who quotes the principle blindly. This thing has to be done this way. Your immediate reply to them is it's very context dependent. The right answer varies. You learned something new? All right. That one wasn't that exciting. Conflicting constructor requirements. Let's use iter-tools. All right. So iter-tools chain takes several sequences like A, B, and C, runs them together as if we were looping over A, looping over B, looping over C, as if they were all one, as if they had been concatenated together. It's a fine tool. The problem is sometimes A, B, and C already come packed together in their own iterable. They are in a, you've got a tuple, or you've got some generator that produces the list A, B, the sequence A, B, and C. So sometimes you want one, and sometimes you want the other. Two different ways of getting to it. So one way is I've got sequences A, B, C. I want that to run. The other time is I have some tuple A, B, C, and I'd like to be able to say a chain, use that tuple, loop over A, B, and C. And in the case of the tuple, it's pretty easy because I can use star to unpack it. However, if I have a generator or something like that, I'd like to be able to supply them in a just-in-time fashion, creating new C's, D's, and E's, depending on the results of our new computations. Which seems weird, but if you look at the Haskell world, you'll see that taking an iterator and feeding it back into itself is the norm rather than the exception. There's lots of good things you can do with it. And so I knew there were good valid use cases. I need this signature because it's convenient, but I need this one for flexibility. That's a problem. Named tuples, the same thing came up. With named tuples, I sometimes like to pass in the individual pieces. Some stock option, its maturity date, its strike price, whatnot. And then sometimes it already comes together in an iterable. You already have the information in a tuple. Let's say you did a SQL query and you get back a list of tuples. You already have the tuple made, so you have to do a star unpacking. Two different signatures. And the most common conflict for signatures is one person on your staff, on your team, is going to demand, my use case is called for positional arguments, that's what the constructor should look like. And the other person says, I already have iterables. That should be the one true signature. Which one is correct?
Yes.
The answer is yes. Both. The correct answer is these people have legitimate use cases for different APIs. You provide both. We provide you the class method decorator so that you can create alternative constructors. We do this all over the place in Python. So dictionary, as a constructor, accepts a list of key value pairs. But sometimes you already have an iterable and you want to set every value to some initial value. So we provide dict from keys. Both of those things construct dictionaries. For date objects, sometimes we can do date to date. That's a perfectly valid constructor. But sometimes we want to construct it from a timestamp. Sometimes we want to construct it from an ordinal. So we have three different constructors. Iter-tools, I have two variants constructors. I have chain, and then I have iter-tools that should say chain from iterable. Point, which is an example of a named tuple, has positional arguments, but also has an underscore make method for taking in a iterable argument. So the design principle it's not on this page. The design principle is whenever you have a need for multiple constructors, the correct answer is to provide multiple constructors. It is very common in companies, even small companies that are supposed to be flexible and dynamic. We only have 5 people in our company, so we have the advantage of agility. Even in small companies like that, there are slight power imbalances amongst the staff. The choice of constructor is often made on the basis of, I'm more senior than you, and I happen to need it as a positional argument, therefore it'll be positional. Who's ever encountered that type of logic in a company? Okay. So power-based decisions are not an appropriate input to API design. All right. You have another choice. I point out, you could do something magical. You could combine and put both in one. Is it the right thing to do? I would suggest not. Learn from our mistakes. We've not done everything well. Min. Min and max are simple enough. Min 1, 2 will take those 2 arguments, search the 2, figure that 1 is lower than 2, and return the 1. Takes positional arguments. But we'd like to be able to give it an iterable. So it's, hey, what is the min of this list? And it loops over the list. That is the actual signature for min. So the question is, what does this code do? Min star args. The answer is, it very much depends on the length of args. If args is of length 3, it'll search args and pull the lowest of the 3. If it's length 2, search the 2, lowest of 2. If it's length 1, it'll pull out the first one and attempt to iterate over it. Not a good thing. Where else have we seen this? This was string formatting. So what does %r, %x do? Well, the answer very much depends on what x is. If x is the number 3, it substitutes in 3. If x is a list, it gets the record of the list. If x is a tuple, it attempts to unpack the tuple, and that tuple would better be of length 1, otherwise you'll get an unpacking error. These were our tragedies and catastrophes. Learn from them. Don't make these mistakes. Bad, 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 bad. Horrid. Guido did it, therefore we should do it too. So why didn't Guido take the time machine and go back in time and fix this?
To teach us a lesson.
To teach us a lesson. We left these out there.
And to fix it, you would need a zero-length tuple.
Yes, which would also cause an error. All right. So for string formatting, we left it in so you could learn from our lesson. However, we provided you with a better alternative. The new string formatting doesn't have this issue. You can make a proper function call. Also, there was a second issue with this API design. It was the % operator itself. What is the % operator used for elsewhere? Modulo. That's the remainder operation. So its precedence is determined by what's appropriate for the modulo operator. So the precedence of it is the same as divide and multiply. That makes sense. Multiply, divide, remainder. The problem is, if we put an expression over here to the right and put 3 squared, 3 star 2, it will do the thing that we probably want it to do. We'll take 3 and square it, and then take the 9 result and print the repr of it. You guys probably need to see this. It's actually, it still blows my mind. All right. So here we go. We've got %r. So I actually give it a whole string. Result, $, a couple exclamation points. %3. That's a logical thing. %3 squared. 9. Fair enough. What does that do? API design catastrophe. When you start overriding operators, remember those operators have precedence. And the precedence may not be designed for your use case. Who thinks that's an atrocity? Who learned from our mistakes?
Could you show us the result of 3 modulo 2?
3 what?
Modulo 2.
Oh, it will be the same as with the times. Oh, I thought. Yes, because modulo is not defined for strings. Okay, fair enough.
But we put a percent inside that string.
And we could go on. You guys can just. The mod operator was bad for several reasons. All right. So, if let's say you're following Twitter, and my buddy Travis comes out and proposes, hey, we need a matrix multiplication operator in Python, you're going to immediately say no, because we'll have to give it a precedence and associativity, and it'll have to do something meaningful for other objects that are other than matrices. Bad. So say no to my buddy Travis.
But ellipsis is added for Travis.
Yes, and a couple other atrocities. Like rich comparisons, which are a problem unto themselves. Okay. Conflicting positional arguments. Do we really only have 15 minutes left in the total time? Okay. So I have exactly 20 minutes left? All right. I'm going to fly through a couple of slides. The dull. Conflicting subclass signatures. Save that for the part of subclass. I would like to go right to other total failures. You guys seem to enjoy this. Okay, API fail. Async core. In the beginning, we slapped together the easiest possible, junkiest thing that did asynchronous programming, but it sort of worked. People thought it was a fabulous thing because async programming is a fantastic way to get high-performance results out of a single thread in Python. So it was not designed around a protocol. Protocol being a standard set of interfaces for async core. That was a mistake. So we hope to, in Python 3.3, introduce a protocol for async operations so that the protocol is an API that applies to multiple different implementations. So ideally, we will come up with a protocol that all async implementations can comply with so that we have one standard way of interfacing. So we should have done that instead of a concrete implementation. Concrete implementation was the first thing we happened to put together. That was the API. We needed to add hooks so that you could override behaviors. We needed configuration options. Remember I said, don't hardwire in pieces? And we should have planned for a rainy day, so we designed for subclassing in mind. And we should have made some of the internals private. We violated all the rules you learned so far. What happened? Users customized it. They reached into the internals. They stylized it. They monkey patched it in non-standard ways. They did it just so they could get the programs to work. They had to do it. It was not their fault. It was ours for crappy API design. What happened to us as a result? We couldn't fix it. When it became clear it was important, we couldn't make a single change without breaking major Python applications. There were a number of tools that use it. It's a catastrophe. What's our solution? We will leave it in Python. We will put a big X on it and say, this is left in as a lesson for what not to do, and we'll introduce a new module, new async core, which follows the new async core API, or protocol. So we'll have a protocol that's a one true protocol, and it will have inputs from people like the Twisted folks. The Twisted folks will give us a lot of feedback based on a decade of their success, so that we will have designed the protocol not as the simplest thing at work, but something that's battle-hardened and proven in the field. We'll take advantage of that knowledge. We will take several other async tools to make sure that they can work with the protocol too. That will give us really good assurance that what the Twisted people recommended was a good idea. So that's a good way to test out. We will use Google Code Search. We'll see what the Java folks did. We'll see what the small folks did. And if our protocol fits in real well with all of those use cases, it's a good affirmation. For this, as for the protocol, for the concrete implementation, what we will do is we will provide hooks so that you can override certain behaviors. Anything that looks like a hardwired behavior, we'll provide an option for it. We learn from our mistakes. All right. Other API fails. Global state. Right. Okay. This says locate, but it should say locale. Locale.set locale. Okay, this one is not our fault. Locale predates Python. It was used in many languages. It's somewhat standard, and it's somewhat bad because whenever you do set locale, you're making a global state change. What's the problem with that? So right click the server, and I'd like to hand out some locale-aware results. I understand that in some countries they have this unusual convention. What's it? About 15 trillion. They have this unusual convention of not using commas to separate their thousands. So I set my locale to their locale to use periods instead of commas, which makes a global state change. I then go to do my print, which is a separate step. You do the set locale, then you do your prints in that locale, and then you serve back the result. Meanwhile, there's another thread serving another request from another country, which has a different locale. And that thread does exactly the same procedure. It does a set locale, and it does a print. Unfortunately, I've got a race condition. And so one can set the locale, the other can set the locale, which will affect the printing of the first. It's a catastrophe. There are very few good answers to this. There are unpleasant answers, like you can do an OS fork, split off the process. You can do an OS system call and have a separate program that has its own namespace. You can lock up the entire system between your set locale and your print, and then restore the locale. As soon as you introduce locks, you've hurt your scalability, you've hurt your response time. There aren't good answers to this. It's bad. Setting the system in code, similar. We added a warnings module. Warnings, you can add handlers for a warning, you can add filters. If you have two different modules that are both modifying the filters at the same time, one says, I want to see all these warnings. The other one says, I only want to see this warning one time. And the other one says, I never want to see the warning. Someone's going to lose. All right, turn asserts on and off. How do you do that? -O. You start Python with the -O option, it turns off asserts. The good thing about that is I've written all these programs with asserts in it that I want out of my production code. The bad thing is I have this wonderful tool called Nose, or PyBack test, that relies on assert to run the test. So if I run it -O, I've killed all my ability to test in production mode.